Have you ever stopped to think about what's actually running things on your phone or, your smart thermostat?
Mhm.
Even the cloud services we use all the time. We're
Mhm.
constantly tapping and swiping, but underneath it all, there's this kind of invisible manager making everything work together.
The silent maestro, you could say.
Exactly. And today we're diving deep into that Maestro, the Linux operating system. We're basing this on the chapter covering the Linux system and operating system concepts by Silberschatz, Galvin, and Gagne.
Right. And our goal here really is to unpack how Linux actually works. We want to go from its, well, pretty surprising origins right through to its complex inner workings.
So things like how it handles tasks, memory, files.
Precisely. Process management, memory allocation, file systems, security, all those core concepts. We'll break them down, try to make them accessible, and show you how these clever design choices pop up in the real world.
Like peeling back the layers.
Yeah, exactly. Peeling back the layers to see the smart engineering inside.
So by the end of this, hopefully, you'll have a much clearer idea of how Linux manages resources so efficiently and, why it's ended up powering such a huge range of devices.
From supercomputers down to tiny embedded systems.
It really is amazing. So let's start at the beginning. Where did this all come from?
Well, it's a pretty humble origin story,
Yeah.
actually. It started back in 1991. A Finnish university student, Linus Torvalds,
Linus Torvalds, right.
he just wanted to create a small kernel for his own computer, which used the 80386 processor. It wasn't some grand plan initially.
Just a personal project, basically.
Pretty much.
Yeah.
But what happened next was fascinating. He made the source code freely available online very early on.
The open source aspect.
Exactly. And that fostered this incredible global collaboration.
Mm.
Developers from all over started contributing. Now, it's important to distinguish here.
Okay.
There's the Linux kernel itself that core code Linus started and the community built upon. But then there's a complete Linux system.
Which includes more stuff.
Right. It bundles the kernel with lots of other necessary pieces, often borrowed from other big projects like BSD, the X Windows system for graphics, and the GNU project's tools.
So it's a real melting pot of technologies.
It really is. And the sharing goes both ways.
Yeah.
Sometimes other systems, like FreeBSD, borrow useful bits back from Linux, too.
That collaboration really is the secret sauce, isn't it? And that leads to distribution.
Yeah, absolutely. If the kernel's the engine, think of distributions as the whole car.
Okay.
They package the kernel, all those system utilities, libraries, maybe a desktop environment, and crucially, package management systems.
Like Red Hat, Debian, Ubuntu,
Right.
those names people might know.
Those are the big ones, yes. Distributions made Linux much more accessible, moving it beyond just hardcore developers.
So what were the guiding principles behind its design?
Well, a huge goal right from the start was UNIX compatibility. Linus wanted it to look and feel like a traditional UNIX system.
Familiar territory for developers then.
Definitely. And related to that was adhering to POSIX standards. That's the set of standards ensuring applications can be easily moved between different UNIX-like systems.
Consistency.
Right. And perhaps most critically, efficiency. Remember, it first ran on PCs with maybe 16 megabytes of RAM,
Mhm.
tiny by today's standards.
Wow.
Yet it scaled incredibly. Now it runs on systems with terabytes of RAM, but it still retains that lean, efficient core philosophy.
Okay, so given those principles, how is a Linux system actually put together structurally?
You can think of it in layers, maybe like those Russian dolls,
Hmm.
or like figure 20.1 in the book shows.
Okay.
At the very core, the absolute center is the kernel. This is the privileged part, running in kernel mode with direct, unrestricted access to all the hardware.
The boss.
Sort of, yeah. Then, wrapped around the kernel, the system libraries. The most famous is probably libic, the C library. These provide the standard functions that applications use to talk to the kernel. They run in user mode, which has more restrictions.
Got it. Kernel libraries. What's next?
On the outside, you have the system utilities. These are all the programs you use for managing the system. Things like ELS to list files or EPS to C processes. Some run just once when you type them. Others run constantly in the background as daemons, providing ongoing services.
And the kernel itself, is it broken into pieces?
Architecturally, the main kernel is what's called monolithic. It's compiled into a single large binary file.
Why do that?
Performance, mainly. Communication between different parts of the kernel is just a fast C function call, not a slower context switch. But, and this is key, it still achieves modularity
Oh.
through loadable kernel modules. We'll definitely talk more about those.
Okay. And the licensing, you mentioned it was free.
Yes, the kernel is licensed under the GNU General Public License, version 2 of the GPL. It's free software, meaning you have the freedom to run, copy, distribute, study, change, and improve the software.
But not public domain.
Correct. The main condition of the GPL is that if you distribute modified versions or software that links against GPL code, you generally have to make your source code available too.
Hmm.
It ensures the openness continues.
Right, the copyleft idea. So let's circle back to those kernel modules you mentioned. They sound important for flexibility.
They are incredibly important. Think of them as plugins for the kernel.
Okay.
They run in that same privileged kernel mode and can add all sorts of functionality. Device drivers are a huge one, but also file systems, network protocols.
So if I get a new graphics card, the driver might be a module.
Exactly. And that's super convenient for developers. They don't have to rebuild the entire kernel just to test their driver. They compile the module and load it.
Saves a lot of time, I bet.
Immense amounts.
Yeah.
And for users, it means the system only loads the drivers it actually needs. When you plug in a USB mouse, the system can load the mouse driver module, unplug it, it can unload it.
Yeah.
Keeps things lean.
Does that affect the licensing if a company writes a proprietary driver?
Ah, good question. Yes, the module system allows third parties to distribute their own drivers, even proprietary ones, as modules, without necessarily having to put their entire driver under the GPL. It's a bit nuanced, but it provides that flexibility.
So how does Linux manage these modules? Is there a system for it?
There is. There are really four key parts. First, the module management system itself within the kernel, which handles loading modules into memory and letting them talk to the rest of the kernel.
Okay.
Second, you have user-level programs, utilities like insmod and romod, to actually load and unload modules. Third, a driver registration system, so modules can tell the kernel, hey, I'm here, and I can handle this type of device or file system.
And fourth.
Crucially, especially for PC hardware with all its variety, a conflict resolution mechanism.
To stop things clashing, like two drivers trying to use the same piece of hardware?
Exactly. The kernel keeps track of which hardware resources, like specific memory addresses or interrupt lines, are already in use. A module has to request the resources it needs, and the kernel checks if they're free before allowing the module to load and use them.
Prevents chaos? What kinds of things can modules register?
Oh, a whole range. Device drivers are the big one. Character devices like keyboards, block devices like disks, network interfaces, but also file systems, network protocols, even formats for running different kinds of programs.
Very extensible. Okay, let's shift gears. How does Linux manage all the different programs and tasks running simultaneously? Process management.
Right. So Linux inherits the classic UNIX model using fork and exec.
Can you explain those quickly?
Sure. Fork creates a new process, which is initially almost exact copy of the process that called it, the parent. Then exec is used by the new process to replace its current program with a completely new one.
And they're separate calls.
Yes, and that separation is powerful. It means the parent process can create a child with fork, maybe tweak its environment slightly, change some settings, redirect input-output, and then call exec to load the new program into that specifically prepared environment. Very flexible.
Interesting. How does Linux view processes versus threads?
This is where Linux is quite elegant, I think. It doesn't actually make a hard distinction between processes and threads internally. It uses a single concept, the task.
A task.
Yes, and this flexibility comes from a system called clone. You can think of fork as just a special version of clone, where the child shares nothing with the parent.
Okay.
But clone takes slags that let you specify exactly what resources should be shared between the parent task and the new child task. Things like the memory space, clone VM, the file system information, clonefs, open files, clone files, signal handlers, clone zhand.
So if you use clone and specify clonevm to share the memory space,
You've essentially created what other operating systems would call a thread. It's a lightweight task sharing the address space with its parent. It's very efficient.
clever. So what defines a task in Linux? What are its properties?
You can group them into three main categories. First, process identity. This includes its unique process ID, PID, its credentials like user ID, UID, and group ID, GID, which determine permissions, and its namespace, which gives it a potentially unique view of the file system.
Okay, identity. What else?
Second, the process environment. This is usually inherited from the parent task and includes things like environment variables, maybe term defining the terminal type, or lang for language settings. It tailors the OS view for that specific task.
And the third.
The process context. This is the dynamic part, the state that changes as the task runs. It includes the scheduling context, saved CPU registers, priority, pending signals, the kernel stack it uses for system calls. Also, accounting info, its table of open files, its current directory, and crucially, its virtual memory context, which defines its address space.
That's the stuff the kernel has to save and restore when it switches between tasks.
Exactly, that's the context switch.
Got it. So with all these tasks potentially ready to run, how does Linux decide which one gets the CPU next? Scheduling.
Right. Scheduling is all about allocating CPU time, and Linux uses preemptive multitasking. It can interrupt a task to run another one.
Does it prioritize?
Yes. There are two main scheduling approaches. For normal, everyday tasks, Linux has used different schedulers over the years, but since kernel 2.6, the default is the completely fair scheduler, or CFS.
Completely fair. How does that work?
It's quite clever.
Hmm.
Instead of giving each task a fixed time slice, CFS tries to give each task a proportion of the processor's time.
Based on priority.
Exactly. It uses the nice value, a number from -20, highest priority, to +19, lowest priority, to weight how much CPU time a task should ideally get.
So lower nice means more CPU time.
Correct. CFS tracks how much runtime each task has had, and tries to run the task that has had the least amount of runtime relative to its fair share. It aims for a target latency, an interval over which every runnable task should get to run at least once.
What's the benefit?
It leads to excellent interactive performance. Your desktop stays responsive even if something heavy is running in the background. It balances fairness really well with the overhead of switching tasks.
Makes sense. What about tasks that need faster, more predictable responses, like real-time applications?
For those, Linux offers real-time scheduling policies based on PO6 standards.
Mhm.
There's first come, first served, FCFS, and round robin.
How do they differ?
They use a priority range from 0 to 99, separate from the nice values. The highest priority real-time task always runs. If multiple tasks have the same highest priority, FCFS runs one until it blocks or exits, while round robin gives each one a small time slice before moving it to the back of the queue for that priority level.
Is this hard? Real-time? Guaranteed response times?
No, that's an important point. Linux provides soft, real-time scheduling. It strongly prioritizes these tasks over normal ones, but it doesn't offer the absolute mathematical guarantees of a hard, real-time system needed for things like, say, flight control systems.
Okay, clear distinction. Now, inside the kernel itself, with potentially multiple things happening at once, system calls, interrupts, how does it stop them from tripping over each other when accessing shared data? Kernel synchronization.
Ah, yes. This is fundamental, especially on multiprocessor systems, SMP. If two different kernel tasks try to modify the same data structure simultaneously, you could get corruption.
So how does Linux prevent that?
It uses several mechanisms. Since kernel 2.6, the kernel is preemptive, meaning a task running in kernel mode can be interrupted. To protect shared data, it uses locking mechanisms. For very short critical sections, especially on SMP systems, it uses spin locks. A CPU trying to acquire a busy spin lock just waits in a tight loop, spins until the lock is free. For potentially longer waits, where spinning would waste CPU time, it uses semaphores, which allow a task to sleep until the resource is available.
What about interrupts? They can happen anytime.
Right. Critical sections might also need to disable interrupts temporarily, although that's costly. Linux also uses a clever interrupt handling strategy, often called the top half, bottom half approach. You can visualize this from figure 20.2.
Okay, walk me through it.
The top half is the actual interrupt service routine, ISR. It runs immediately when the interrupt occurs, does the absolute minimum work needed, like acknowledging the hardware, and generally runs with further interrupts of the same type disabled. It needs to be fast.
And the bottom half.
The top half schedules the bottom half, also called softerics or tasklets, to run later with all interrupts enabled. The bottom half does the more complex, time-consuming processing related to the interrupt. This separation prevents the system from being unresponsive because it spent too long handling one interrupt.
Neat. And all this locking and synchronization has evolved to work well on machines with many CPUs.
Yes, SMP support has been a major focus. Early Linux had a big kernel lock, BKL, which wasn't very scalable. Modern kernels use much finer-grained locking with spin locks and other techniques to allow many parts of the kernel to run truly in parallel on different CPUs.
That makes sense. Let's move on to another critical resource, memory. How does Linux manage that? Memory management.
It's handled in two main parts, managing the physical RAM chips and managing the virtual address space that each process sees.
Let's start with physical memory.
Okay, Linux divides physical memory into different zones. The exact zones depend on the hardware architecture. For example, on older 32-bit by 86 systems, like in figure 20.3, you might have zone edema for old devices that can only access the first 16 member, zone normal for most regular memory, and maybe zone HAMM for memory above 1 GD that the kernel couldn't directly map all the time. 64-bit systems usually have a much simpler layout
Why
to
zones?
manage hardware limitations and allocation policies. Memory within these zones is managed in units called pages, usually 4 KB. The main allocator for groups of pages is the buddy system.
How does the buddy system work? Let's say I need 4 KB.
Okay, imagine the allocator only has a free 16 KB block, as shown visually in figure 20.4. It splits the 16 KB block into two 8 KB buddies. It then takes one 8 KB block and splits that into two 4 KB buddies. Now it has a 4 KB block to satisfy your request. The remaining 4 KB and 8 KB blocks are kept on free list for their respective sizes.
And when I free the 4 KB block?
It checks if its 4 KB buddy is also free. If it is, it merges them back into an 8 KB block. Then it checks if that block's 8 KB buddy is free, potentially merging them back in the original 16 KB block. It's efficient at reducing fragmentation.
Clever. What about smaller chunks of memory inside the kernel?
For that, Linux uses the slab allocator. This is optimized for allocating memory for common kernel data structures, like the structures that hold process information. Think of figure 20.5.
Okay, what am I picturing?
Imagine you frequently need, say, 7 KB chunks for some structure. The slab allocator creates caches for objects of that size. Each cache contains slabs, which are typically one or more contiguous physical pages. Each slab is carved up into multiple fixed-size objects, in this case 7 KB objects.
So it pre-allocates.
Exactly. When the kernel needs a 7 KB object, the slab allocator can quickly grab a free one from a partially filled slab. When it's freed, it goes back to the slab. This avoids the overhead of the buddy system for frequent small allocations and improves cache performance because objects of the same type are kept together.
Very optimized. And you mentioned the page cache earlier.
Yes, the page cache is vital. It's the kernel's main cache for data read from or written to files and block devices. It's tightly integrated with the virtual memory system, making file I/O very efficient.
Okay, so that's physical memory. What about virtual memory, the address space each process thinks it has?
Right. The virtual memory system gives each process its own private linear address space, independent of others. It manages the mapping between these virtual addresses and physical pages in RAM, or pages stored on disk.
How does it track these mappings?
It maintains two views. A logical view, which sees the address space as a collection of non-overlapping regions called view-mera structs, often organized like a balanced tree. Each region defines properties like start and address and permissions, read, write, execute. And then there's the physical view, which uses the hardware's page tables to track exactly where each virtual page is currently located in which physical RAM page, or if it's been swapped out to disk.
Where do the contents of these virtual pages come from?
They have a backing store. It might be demand zero memory, meaning the page is just filled with zeros the first time it's accessed, or it could be file-backed, where the memory region is essentially a window onto a portion of a file on disk.
Can processes share memory?
Yes. Mappings can be private, where changes are local using copy on write, or shared, where modifications made by one process are immediately visible to others sharing the same mapping.
How does this tie into fork and exec?
When you exec a new program, the kernel essentially throws away the old address space and sets up a fresh one based on the new program file. When you fork, the kernel cleverly duplicates the parent's virtual memory structure, or various structs, and page tables, but initially marks the underlying physical pages as shared and read-only.
The copy on write trick again?
Exactly. A physical page is only actually copied when either the parent or child tries to write to it. This makes process creation incredibly fast.
What if the system runs out of physical RAM?
Linux uses paging. It doesn't swap out entire processes, just individual pages. It needs to choose which pages to move from RAM to a swap area on disk to make room. The policy it uses is a variation of the clock algorithm, or second chance, which tries to approximate a least frequently used LFU approach by tracking how actively pages are being accessed.
Okay, and when you actually run a program using exec, how does Linux load it?
The kernel handles loading the program executable. It reads the file header to understand the format. Linux supports several, but the modern standard is ELF, executable and linkable format. It then sets up the initial virtual memory mappings for the different segments of the program.
Like the code and data.
Right. If you visualize the typical ELF memory layout, like in figure 20.6, you have the stack at the top of the address space growing downwards. Then usually memory mapping segments for dynamic libraries. Below that is the program's executable code, text segment, usually read-only, then initialized data, then uninitialized data, the SS segment, which is demand zero. There's also a heap area that can grow upwards for dynamic memory allocation using malloc.
Does it load the whole program into RAM immediately?
Not usually. It uses demand paging. The pages for code and data are only loaded from the executable file on disk into physical RAM the first time the process actually tries to access them.
Efficient. What about libraries? Static versus dynamic linking.
Right. With static linking, all the library code the program needs is copied directly into the final executable file. It's simple but wasteful if many programs use the same library.
And dynamic linking.
With dynamic linking, the program executable only contains references to the libraries it needs. When the program starts, a special dynamic linker loader finds these libraries on the system, if they aren't already in memory, and maps them into the process's address space. This saves disk space and RAM because the library code is loaded only once. It often uses position-independent code, PIC, so the library can be loaded at any address.
Very cool. Let's switch to how Linux manages files. The famous Unix philosophy, everything is a file.
Yes. This is a really powerful abstraction. Whether it's a document on your disk, your keyboard, a network connection, or even kernel data structures, Linux tries to present it through the file system interface.
How does it achieve that unified view?
Through the virtual file system, or VFS. It's an abstraction layer between the user applications and the concrete file system implementations.
How does VFS work?
It uses an object-oriented approach. It defines common object types that represent file system components. The inode represents an individual file or directory. The fill represents an open file handle. The superblock represents a mounted file system. And the dentry represents a directory entry or path component. Each object type has a table of associated operations functions like open, read, write, close.
So the VFS knows the generic operations, but not the specifics.
Exactly. When an application calls, say, read on a file descriptor, the VFS looks up the read function associated with that open file, fill object, and calls the specific implementation provided by the underlying file system, like X3 or NFS or whatever. It acts as a dispatcher.
Clever. It hides the details. What about performance? Looking at path names like us include a Studio H seems like it could be slow.
It could be, but the VFS uses a dentry cache, directory entry cache, to store the results of recent path name lookups. So translating paths into inodes is usually very fast.
Makes sense. What's the standard Linux file system most people encounter? XT3 or XT4?
Historically, XT3 was dominant for a long time, evolving from X2, which itself evolved from earlier systems. Now, XT4 is very common. They share similarities with the Berkeley Fast File System, FFS.
Like how data is laid out.
Yeah, using data block pointers in the inode, indirect blocks for large files, similar directory structures. X34 tend to use smaller allocation units than FFS, though. For performance, they try to cluster related data together using block groups, which are similar to FFS's cylinder groups.
How does it find free space when writing a file? Is it smart about it? Thinking of figure 20.7?
It tries to be. It attempts to allocate blocks physically close to the file's other blocks. It uses techniques like pre-allocating a small number of blocks, maybe 8, when a file grows, hoping they'll be contiguous and used soon, reducing fragmentation.
A key feature of X3 and X4 is journaling. What problem does that solve?
Consistency after crashes. Before journaling, if the system crashed midway through writing file data and its associated metadata, like inode updates, free block maps, the file system could be left in an inconsistent, corrupted state. You'd need a lengthy file system check on reboot.
And journaling fixes that.
Yes. With journaling, before the file system makes changes to its main structures on disk, it first writes a description of those intended changes sequentially to a dedicated area called the journal.
Like a log.
Exactly, like a log or diary. A set of related changes is called a transaction. Once the transaction is safely written to the journal, the file system can then apply the changes to the main file system structures.
What happens if it crashes during the update?
On reboot, the recovery process just reads the journal. If it finds committed transactions whose changes weren't fully written to the main structures, it simply replays those changes from the journal. If it finds incomplete transactions, it just ignores or undoes them. The result is a consistent file system very quickly.
That sounds much faster than a full check. Does it help performance too?
Yes, especially for operations that involve many small scattered metadata writes, like creating or deleting lots of small files. Journaling turns those potentially random writes into faster sequential writes to the journal log.
Very neat. Another interesting file system in Linux is proc. It's not really a disk file system, right?
Correct. Proc is a virtual file system. Its contents, the files and directories you see when you soundbells proc, aren't stored on any disk.
Yeah.
They're generated on the fly by the kernel when you access them.
What's it used for?
It's a window into the kernel soul. It provides information about running processes. That's where the EPS command gets its data. System hardware, memory usage, kernel statistics, network configurations, tons of stuff.
Like procwinfo or procmeminfo?
Exactly those. And what's really powerful is that some files under processes are writable. By writing values to these files, you can actually tune kernel parameters while the system is running.
Wow, dynamic configuration through the file system. Okay, let's talk input and output. I/O, how does Linux handle devices?
Following the everything is a file idea, device drivers mostly appear as special files in the dev directory. You interact with them using the standard file system calls, open, read, write, ioctil.
Are all devices treated the same?
Not quite. Linux groups them into three main classes, as shown in Figure 20.8. First, block devices.
Like hard drive.
Yes, hard drives, SSDs, CD-ROMs, flash drives. They allow random access to data in fixed-size blocks. They're typically used to hold file systems, but applications like databases might access the raw block device directly for performance.
Is I/O scheduling important for them?
Hugely important for performance. Linux has an I/O scheduler layer that manages the queue of read and write requests for block devices, trying to optimize throughput and latency. The default scheduler for many years now has been CFQ, completely fair queuing.
Related to the CFS CPU scheduler.
In spirit, yes. CFQ aims for fairness at the process level. It maintains separate I/O request queues for each process and serves them in a round-robin fashion, giving each process a slice of the disk bandwidth. This stops one I/O-heavy process from starving others, improving overall system responsiveness.
Makes sense. What's the second device class?
Character devices. These handle data as a stream of bytes, typically sequentially. Think mice, keyboards, printers, serial ports. The kernel usually passes requests directly between the application and the device driver.
Any special cases?
Terminal devices are a big one. They have complex line disciplines that handle things like input editing, buffering, and flow control.
And the third class?
Network devices. These are handled differently. You don't typically interact with them via dev files. Instead, communication goes through the kernel's networking stack using socket interfaces.
Okay, so processes need to communicate inter-process communication, IPC. What mechanisms does Linux provide?
There are mechanisms for synchronization and for data transfer. For synchronization, the simplest is signals, used to notify a process of an event. They carry very little information, though. Internally, the kernel uses wait queues for tasks to pause until some condition is met. Linux also supports System V semaphores for more complex synchronization between multiple processes.
And for passing data between processes?
The classic Unix pipe is one way a parent creates a pipe, forks, and then the parent and child can communicate through it. For higher performance, there's shared memory.
How does that work?
Processes can map the same region of physical memory into their virtual address spaces. Any data written by one process is instantly visible to the others. It's extremely fast.
Any downsides?
No built-in synchronization. You need to use signals or semaphores alongside shared memory to coordinate access and avoid race conditions.
Got it. You mentioned the networking stack earlier. Can we delve into that a bit? Linux is obviously huge in networking.
Absolutely crucial. Linux supports a vast array of network protocols. Internally, the network structure has roughly 3 layers. At the top is the generic socket interface, providing the API applications use, like the BSD sockets API. Below that are the specific protocol drivers TCP, UDP, IP, etc., which implement the logic for each protocol. And at the bottom are the network device drivers that talk to the actual hardware network cards.
How does data move between these layers?
Primarily using special data structures called SCUFs, or socket buffers. They're designed to be efficient, minimizing data copying as packets move up and down the stack by using pointers to manipulate headers and data within a contiguous buffer.
And the TCP/IP suite.
It's all there. IP handles routing packets between networks using a routing table, the FIB. UDP provides simple, connectionless datagrams. TCP provides reliable, connection-oriented in-order delivery, managing acknowledgments and retransmissions. ICMP handles error reporting.
What about security features like firewalls?
Linux has a built-in packet filtering framework. Netfilteritables, historically now often NF tables. It allows defining rules organized into chains for input, output, forwarded packets to inspect, modify, accept, or drop network packets based on various criteria like source and destination address, ports, protocol state.
Okay, last major area, security. How does Linux protect the system and user data?
It builds on the standard Unix security model, primarily focused on authentication, verifying who you are, and access control, determining what you're allowed to do.
How does authentication work? Logging in?
Traditionally, it used a publicly readable file, etc. password, storing usernames and hash passwords. Modern systems use shadow passwords, where the hashes are kept in a separate protected file,
Mm-hmm.
etc. shadow. But the real key today is PAM pluggable authentication modules. Yes, PAM is a flexible framework using shared libraries. Instead of hard-coding authentication logic into every program like login or SIsh, these programs talk to the PAM library. PAM, basic configuration files, then call the appropriate backend modules to handle the actual authentication. Could be the standard password check, could be LDIP, Kerberos, fingerprint readers, two-factor auth, anything.
So it makes it easy to add new ways to log in.
Exactly. It's incredibly flexible for administrators. PAM handles not just authentication, but also account management, like password expiry, session setup, and password changing rules.
Okay, once you're authenticated, how does access control work?
It revolves around numeric identifiers, user IDs, UIDs, and group IDs, GIDs. Every file and resource has an owner UID and a group GID. Every process runs with a specific UID and one or more GIDs.
And permissions.
Files have permission bits defining read, write, and execute access separately for the owner, the group, and everyone else. World. The kernel checks the process's UID and GIDs against the file's UID, GID, and permission bits to decide if access should be granted.
Is there a super user?
Yes, UID 0 is the root user, traditionally bypassing most permission checks.
What about programs that need temporary privileges, like the print command needing special access?
That uses the set-to-id mechanism. If a program file has the set-to-id bit set, when a user runs it, the process runs with the file owner's UID, its effective UID, not the user's real UID. This allows carefully written programs to perform privileged operations. Linux also have enhancements like a save set user ID, so a process can temporarily drop privileges and regain them later for better security. It also has separate file system UIDs, suited, for finer control over file access rights, particularly useful for servers acting on behalf of users.
Seems like a robust, layered approach to security.
It is, while not perfect, the traditional UNAX model, enhanced by Linux features and things like PAM, provide the strong foundation.
Wow, we've covered a lot of ground from Linus Torvalds' initial project to the complexities of scheduling, memory management, file systems, networking, and security. It really shows how these intricate parts form this incredibly versatile operating system.
Yeah, it's a journey through some really elegant engineering. Hopefully, looking under the hood like this helps you see Linux not just as, this black box, but as a system where deliberate design choices about how to manage resources really impact the efficiency and reliability we depend on every day. It's a huge testament to what collaborative open development can achieve.
Absolutely. It leaves you wondering, given Linux's core design, its openness, its adaptability, what future challenges might it be uniquely suited for? Think about things like quantum computing, maybe, or even integrating technology more closely with biology. Could the fundamental principles of Linux evolve to tackle those kinds of frontiers in the decades ahead?
That's a fascinating thought. How would concepts like processes, files, or even scheduling adapt to radically different computing paradigms? It's definitely something to ponder.